So machine learning can be broken down into roughly 3 different types of learning. One is supervised learning, second is unsupervised, and third is reinforcement learning. A researcher at Google once said he kind of imagines this as a cake, where the top layer is supervised learning, the middle layer is unsupervised, and the bottom is reinforcement. When you think about how kids learn in one of these 3 ways. So unsupervised learning is simply you show a picture of a cat and the word cat, picture of a dog, the word dog, and so on. Unsupervised learning is where kids try and figure out a pattern on their own. In Sesame Street, there's this thing with like one of these things does not belong here. That's unsupervised learning, basically. And then reinforcement learning is where you actually punish somebody for getting a wrong answer and reward them for getting the right one. And you do this all the time with kids. Sometimes it's autonomous. For example, if they burn their fingers, that's clearly reinforcement learning. So within supervised learning, there's 2 types. There's classification models, and then there are regression models. So classification, think about them as they're actually variants of the same thing. Classification is discrete, and regression is continuous. So classification, you have diagnostics, image classification, fraud detection. These are all things that can be put under classification problems. Regression could be things like market forecasting, network prediction, determining life expectancy. So the difference is that with classification, you're put into one of X number of buckets where X is an integer, whereas regression is simply figuring out a value between 0 and a million, which could be a real number, and so it's not a clear classification type of problem. But they're all kind of there are variants of each other. So think about it as classification is discrete, regression is continuous. Unsupervised learning, there are kind of 2 types broadly. There's clustering and there's also dimensionality reduction. Clustering could be things like customer segmentation, targeted marketing. Dimensionality reduction could be structured discovery, which means that because a lot of times humans can only see in 3 dimensions, but a lot of systems exist in many, many dimensions. An example could be determining a customer exists in many dimensions. So for example, they have an age, they have a sex, they have where they come from, or what area of the city they come from, what their occupation is. There are a whole bunch of factors. Each of those factors essentially translates to a dimension. And it's very hard for humans to see more than a couple. And so dimensionality reduction is about simplifying it so that you can actually see the real structures involved. Data visualization, same thing, same idea, essentially, because if you have a complex 3-dimensional or 10-dimensional graph, how do you want to translate that into a 2-dimensional graph, which is easy to view? Now, all of these cases, you do lose some information, so it's not like, because anytime you reduce dimensions, you do kind of lose some information, but overall, dimensionality reduction kind of works there. The other area clearly is compression, because that's another way. For example, instead of working with 20 different features, you work with 10, and from those 10 features, you could either those 10 features you derive the original structure, or you can. But I should say it's lossy compression in this case. Reinforcement learning is used a lot in game AI, skill acquisition, and robotics. So classic examples of that would be AlphaGo. Is a reinforcement learning problem. It's effectively you teach an AI how to play a game and do it well. So AI Studio itself, there is a reinforcement learning component to get it to solve the problem of building machine learning models more efficiently over time. So there are many types of tools and frameworks. Some of you may have used some of these in the past. What these all have in common is, some of them I like, some of them I don't. I absolutely hate Caffe. It's like I think the person who invented it should be censured in some way. It's a very painful framework to use. TensorFlow is by far the most universal, and in fact it is becoming a de facto standard There are actually now TPUs, tensor processing units, which essentially encompass the math behind TensorFlow. The Microsoft Cognitive Toolkit, this has become their new, this was their newest, they kind of unified a lot of their machine learning solutions under the MCT. PyTorch, of course, Piano, and MXNet. MXNet is Amazon's thing. But by far the easiest is, the most common one is TensorFlow. TensorFlow Keras is now part of TensorFlow as well, so people have used Keras in the past, and still do. It's one of the most commonly used ease of use frameworks. The challenge with all of these, however, is that you need to know about deep learning, and you need to understand enough about deep learning to solve problems. And the problem with understanding deep learning is that, sure, on one hand, you can learn certain patterns that, okay, for example, I can use a convolutional neural network for this problem, or an LSTM for this, or something like that. But that doesn't necessarily help you. That doesn't necessarily give you the best models you can get. There's a lot of, for example, hyperparameter tuning. There are a lot of other things that need to go on. And you're not, even the choice of algorithm may not necessarily be perfect. So determining what set of algorithms to use and what set of hyperparameters, it's actually more of a art than a science. There's no clear way to solve that problem. Well, there's no clear objective way to solve that problem. So what AI Studio does is it has developed approximation methods to determine what the best algorithm to use to solve certain problems are. But it's something where it is still pretty much an art. So the difference is that AI Studio is able to do it a lot faster. And I believe it's like something between 700 to 900,000 algorithms currently within AI Studio, which is basically beyond most humans. So this would be something where we can, yeah. So the next thing is to understand the anatomy of a machine learning project. Firstly, it's obvious AI models need to be trained. That goes without saying. The training data is called the ground truth. That's another word for training data. So large amounts of data need to be prepared to train models. The thing about the ground truth, though, is that your model can only be as good as your ground truth. For example, with medical systems, can you ever build a system that is better than doctors? Well, than all doctors? Probably not. The reason is that it's ultimately limited by how good the original training data was. If doctors make mistakes, guess what? Your machine will make the same mistakes. So determining the right algorithm and the right algorithm parameters is hard. It's a very hard problem, determining the right set of hyperparameters and the right set of models. But the overall process is the same. So the first thing is identifying the problem. So determining basically what problem to solve and whether or not it's even solvable using machine learning. That's a very hard, that's actually not so trivial to understand whether or not something is a machine learning problem or not. A lot of times when we talk to customers, they talk to me about something, and it turns out, well, you know what, why don't you just do a search in a database? That'll give you the answer. So for example, they're saying, we'd love to, for example, find all customers within a certain income category. And I was like, well, you do have that information in your database, right? It's a simple search. So determining what's a machine learning problem or not is something that's actually not always straightforward. The training data is another thing. There are a lot of really cool problems out there. Whether or not you have the training data for that is a fundamental restriction that is placed on whether or not you can build a model around that. There's an ongoing research project. Well, there are a lot of research projects currently underway to figure out how to reduce the amount of training data. So, for example, there's a method called one-shot learning. So one-shot learning is a way to reduce the amount of training data needed, but it always comes at a compromise. So, for example, reducing the amount of data needed to train comes at the cost of reducing the accuracy of your model. One that recently was developed by Jeffrey Hinton called capsule learning is also something where it is you reduce the amount of data that's needed to train. So the next thing is understanding the algorithm. So determining the right set of algorithms, as we talked about, is relatively hard. And part of the algorithm are understanding the algorithm parameters, like the hyperparameters involved. The next part is training the model. So training the model is it's not as easy. So on one side, yeah, sure, just once you start training it, you just get it to go, and the machine will take over, and like 2 days later, you've got your answer, or you have your model. But it gets more complicated. So, for example, training the model could be, can training this model be parallelized, or does it have to operate in a serial way? Is it possible to run in a distributed mode? Is it an analytic method versus a deep learning method? And both occupy different amounts of time and computational resources. So understanding, for example, the batch sizes to use, understanding the limitations of the machine, like how much memory you can actually, how much memory the machine has, determining other performance characteristics of the machine will all determine how fast your model can be trained, and also, to some extent, whether your model can be trained. That is a key thing. So an example would be, if I'm analyzing video, it turns out that to build a very good video classification model is pretty hard. It takes a lot of compute resources beyond what most machines have. The next question that you have is that, okay, great, I've trained a model, but where is it running? If it's running on a low-power machine or low-power device, there are certain considerations I need to make as part of the training process. So, for example, it may, for example, constrain the algorithms I'm using. It could also be that, there are other factors I need to consider in terms of like how much and how the model is actually constructed. Finally, the evaluation of the model part is this is where you take a model and you determine how good it is or how bad it is. And the challenge there is typically what you do is you divide up your data into training and validation data. But that's not enough, because the problem is that your validation data, if your training data has a bias, chances are your validation data does too. So when you then take data in from the wild, sometimes you get some very strange results. You find that your model doesn't predict anything, and you're wondering, like, why is that the case? And there are many examples of this. It could be that training the data from the wild has more noise, in which case then what you need to look at is are there ways to reduce the noise? Classic example is somebody built a model to detect horses, and it was like determining the type of horse. And it turns out that with the training data it was pretty good, but then when they started to look at images in the wild, it turned out what the AI was really learning was it had fixated on the copyright. There's a copyright symbol there, so it had learned the copyright on the model. And when images from the wild didn't have that copyright symbol, then it got confused. So there are many examples of that. So another example, this might be, the Americans built a system that could tell the difference between a Soviet tank and a US tank. And so they fed it pictures of US tanks and pictures of Soviet tanks, and sure, in the training, with the data that they were presented to the machine did in fact pick out the differences and did it quite consistently. So then they went out into the Mojave Desert and they put out cutouts of the various tank types and see whether the machine would be able to learn. And it turned out that it predicted everything as being an American tank. And they were wondering, like, okay, well, this is weird. And it turns out that the pictures that they presented of Russian tanks were all cloudy. So it had learned to tell the difference between cloudy and sunny. So part of that is when you evaluate the model, you need to test it with data from the wild to see whether it's really working. Then finally, deployment of the model. So that's, again, a challenge because an example would be we're working right now with a microchip company to essentially run our models on FPGAs. Which basically means that you're now extremely limited in terms of memory and performance of the chip. So how do you then deploy the model onto that? You can't just simply train an arbitrary model and try and squeeze it in because the memory constraints are fairly limited. So you need to think about that as part of your deployment strategy. Like, where do you plan to deploy it? Is scaling an issue? Are you looking at being able to are you going to be looking at scaling out or scaling up the machines? All these things are things to think about. So for the cost of machine learning, there are many different components of that. People is definitely one. The resources, there are only about 10,000 people in the world today, by one estimate, who really understand deep learning. And the challenge is that enterprises, companies, when they hire somebody who claims to have a deep learning background, you change the problem slightly, and then they can't solve the problem anymore. And part of that is because of the fact that two problems that look very similar could actually require very different architectures and designs. But a lot of that, you need to understand the underlying math to be able to determine why one is better than the other. In fact, when we talk about LSTMs and recurrent neural networks later on, you'll see that there is a very, very strong mathematical component to really understanding, like, well, why does an LSTM work in this scenario versus an RNN and so on, like a standard RNN. Compute is obviously a cost factor. Data generation is a cost factor. The time it takes. One of the challenges that enterprises have is that if it takes a long time to build a model, so iterating on a given model one of the things is that you never build a model from start to finish and you're happy with it. You're always going to be iterating on it. And even once you've trained it, chances are it may need to be retrained sometime later because your ground truth has changed. So if you have a long training time, or if you have long development time, that's a problem. And it turns out that machine learning is particularly bad as far as this is concerned because it takes a long time to determine what the right set of algorithms are, and even when you determine that, it can be a challenge. So finally, the last part is management. It's something you don't really think about much today, but these would be things like version control, data provenance, where did the data come from? How do you know that, like, one way to hack a deep learning system would be to change the underlying data that was used to train it. And how do you tell whether your model has been hacked or not? Then there are just questions. There are questions of version control. Is your model, like, which version are you actually using? Do you have metrics associated with accuracy and all these type of things? These are all considerations when you think about management of the model. Okay, so what is the criteria for a good machine learning problem? The first thing is motivated by a real-world problem. A lot of times you see toy box problems. These are not good machine learning problems because how do you adapt them to kind of realistic scenarios? An example would be that if there's a lot of heavy processing involved in the data before it can actually be used in your model, that's not a good machine learning problem. That's more like a toy model because doing that heavy processing of your data is unrealistic in a production setting. So you need to kind of look at a real world problem and look at, well, how does my data get to the system? What amount of pre-processing do I need in order to get my data to a point where I can use my model with that? And so when you build your training set, if your training set is too curated, if it's too modified, chances are the underlying model is not going to be that useful. So what you need to look at is, okay, well, what is a realistic scenario? When I'm getting real data, it's noisy. Real data could be noisy. It could have all kinds of issues associated with it. There are various ways to hack models as well, so you can imagine that people will be utilizing these as well. So for example, there's something called an adversarial attack on images, which I'll talk about. It's one way to, for example, hack a system. There are all these things that you need to think about. Well, how do I ensure that the underlying system, that what I'm trying to train it on, is realistic. So it's well defined. So the key questions you need to ask is kind of obviously, what is the problem? Interestingly enough, another question is, why does the problem need to be solved? It sounds like, well, why is this a machine learning question? I mean, shouldn't this be a business analyst question? Well, the answer is it's both. And why the problem, in terms of why does the problem need to be solved, it's a way for you to look at, is it possible to simplify the problem into something that is easier to solve? An example could be that somebody's trying to figure out, a good example is like when to put ads in the TV show. That's a hard problem to solve, even though that's motivated by a real problem. But why do you need to solve that particular problem? And so when you kind of understand the exact business reasons, chances are you're also going to narrow down the scope of the problem. This is basically what this is ultimately trying to do, is to narrow down the scope as much as possible. So a machine learning problem that has too broad a scope is not likely to be solvable, or if it is, the results are going to be really poor. So narrow down the scope as much as possible. So don't try and boil the ocean, as they say. A good example would be in the medical space. I'm working with one group right now in Essen, it's in Germany, where they're looking at determining whether there are pathologies in some images. The thing is, if you look at the whole body, that's too big a problem, because there are many things that can go wrong with the human body. If you concentrate down to a specific part of the brain, that's a much more scoped down problem, and your chances are you're actually going to get something meaningful out of that. And then the second thing is that, well, I'll talk about the second thing later. But essentially, asking the question, why does the problem need to be solved? The question comes down to, like, how actionable is it? Is it something I can make a decision on? Is it something that's really useful? Is the scope small enough, and so on? The next question is, how would I solve the problem? Which means that, do you have a methodology that you're going to use? Is there a way for me to solve the problem using the data that I have? So that's a question that you can ask. The other thing that is oftentimes the case is, can this be mapped to a known machine learning problem? One of the things that they were initially talking about, so when I talked to the physicians in Germany, they were looking, well, this sounds a lot like a clustering problem, and it was not. It was a classification problem, but you can map it as a classification one. A really great example, actually, that just came up, is we can now do classification of molecules, and so, for example, determine whether molecules are toxic or not. And it turns out that this is very similar to a text classification problem, and and so you can actually map that onto a known machine learning problem. So there are many types of things like that. If you can actually map a problem into something that's already understood, it simplifies your problem a lot. Another example would be audio recognition. So recognizing audio in the end turns out to be nothing more than image recognition, because you're analyzing the spectrogram of an audio recording. Then the next one is obviously enough data, high quality data, and it should obviously reflect the ground truth. And going back to how much modification am I doing to my data before it actually gets to my training model is a part of that. If your training set is highly curated, as I said, your model may not necessarily represent anything.